All right, hello everybody. Welcome to the second part of the video for section 4.2. We're continuing on today looking at ideas of doing different types of approximations using calculus, and we'll do a little bit more with linear approximations today. We're going to kind of expand our understanding of that and start to look at error a little bit closely. So what are sorts of errors or amounts of error come up in these approximations? Okay, so first going to draw a graph here, and try to draw it large enough so that we can see everything we need to see. So I'm going to have a couple of sets of axes right here in the black, and then I have a function that I'm going to draw in blue here. Okay, I'm going to call this function f of x. And I'm going to identify an input value for that function. I'm going to call that input value x sub 0. Okay, and you'll often see this, and maybe in physics you've seen this called x naught. It's really common when we're using that as like a starting point. So that's why I have the x sub 0. And then I'm going to go a little bit further along the axis to another point that I'm going to call, well, actually, before I call it what it is, I'm going to call this distance between these two. Okay, from here to here. I'm going to call that delta x. So this triangle here that I'm trying to draw, that's supposed to be a delta x. Okay. And if I do that, then this new point we've got here, well, hopefully you agree with me, it would become x sub 0 plus delta x. Right, because notice, all we're doing to go from the first point here to the second one is we're taking this input value, this x sub 0, we're adding the delta x amount, whatever amount that is, and that'll give us our second point right here. Okay? All right. And then I'm going to look at the output values of each of these. So for x sub naught, we see that the output value would be somewhere up here. Let me try to draw that better. So that'd be here. And then and actually on the axis over here, let's call this f of x sub naught. Okay. And the output value for x sub naught plus delta x, that's going to be up here somewhere. And so that would be a value here, and we'll call that f of x sub naught plus delta x, right? Because for each of these points, we find the outputs by just taking the point, the input value, plug it into the function. And then I'm going to call this difference between these two. Okay, so the difference between f of x sub naught and f of x sub naught plus delta x, we're going to call that delta y. Okay, which hopefully isn't too surprising because, well, first of all, the term delta usually means, or the symbol delta usually means change in. So if we're looking at the distance between the two outputs, that would be the change in y. That's why down here along the horizontal axis, we call the distance between x sub naught and the second point delta x because it's a change in x or inputs, right? Okay, now the next thing I'm going to do then is add in the tangent line at the point x sub naught. Okay, so that's going to look like this, sort of. My best effort at it. Actually, that was terrible. Let me try again. Okay, so it'd be like that. And if you recall, prior to this, we were using the tangent line to approximate values on the function, right? So we could do a similar thing here with the ideas of the delta x's and delta y's we were just looking at. So notice that on the tangent line, well, the output for x sub naught is still the same, but the output for x sub naught plus delta x is going to be a little different now. It's going to be a little bit, in the way I've drawn it here, it'll be a little bit higher up. It'll be up here, right? And so we're going to have a different name for the difference between the output value for x sub naught on the tangent line with the output value for x sub naught plus delta x on the tangent line. So that's going to be the distance from down here up to here now. We're going to call that dy. And again, that's more of an estimation now, right? Because in this case, we're actually using the tangent line to estimate the output value for x sub naught plus delta x. And so that dy is going to be an estimation for delta y, right? It's not going to be exactly the same, as you can see from the calculation there. But it'll be very similar, or pretty close. The other thing we'll look at is, because we have dy as the distance between the output value for x sub naught and output value for x sub naught plus delta x on the tangent line. We're also going to have this value dx, which will be the distance between x sub naught and x sub naught plus delta x, kind of in the thinking about it related to the tangent line. However, notice that that distance isn't different than delta x, right? So these two things are actually the same. Whew. Okay, that was fun. All right, so let me pull up a much better drawing of this. So this is from a textbook. And notice it's got all of these same things labeled out. I'm going to add here in the picture that we're calling this point here x sub naught, not just x, okay? And again, we see from this picture that the dx and the delta x, those are the same. We see the delta y as the differences between the output values on the original function, but then dy is the difference on the output values on the tangent line. Okay, and so what we want to do now is come up with some formulas for these. And first I want to point out that for the tangent line, I'm going to call that L of x. In our previous video, we came up with a formula for that, right? So if our starting point is x sub naught, then based on what we found out in the previous video, the formula for the tangent line here is f of x sub naught plus f prime of x sub naught times x minus x sub naught. Okay, so you recall that, check back in your notes, check back at the previous video, we saw that. All right, so let's use this now to find a value for dy, or a formula for dy. And again, dy is that estimation of the difference in the output values using the tangent line, right? Well, dy is going to be the distance between the output value up here at the point they're calling R and this point down here at P. Well, what's going to be the output value at the point R? Well, that's if we take this x sub naught plus delta x and we plug it in as an input for the tangent line, which using this formula here, what that's going to give us is f of x sub naught plus f prime of x sub naught times, now this value here is our input, so that's replacing x, so that's going to take the place of x here, and Darn it, I'm going to have to go on to another line. Hold on, let me do this instead. Write it down here. So dy is f of x sub naught, right, plus f prime of x sub naught times, and then inputting for x, we're going to have x sub naught plus delta x minus x sub naught. Okay, because this x sub naught plus delta x is just taking the place of the x here. And then we're trying to find this distance dy, so we need to subtract the output value of x sub naught, which we know is just f of x sub naught, right? Because that is right on the function. Okay, well, looking at this, some things will cancel, right? So we see we have an f of x sub naught here and minus f of x sub naught here, so those two things will cancel. Inside of our parentheses here, notice there's an x sub naught and a minus x sub naught, so those will cancel. And when we do that, we end up with dy equals, and we're just left with f prime of x sub naught times delta x. Okay, so that's all that's left over. And then we're just going to do one more thing with that. Since we were dealing with the tangent line there, we actually don't want to use delta x because that has to do with the original function. So we're going to replace the delta x with the dx since they're the same. So we end up with dy equals f prime of x sub naught times delta x. Okay? And that's more or less our formula for that. Now there's one more thing I want to say about that. Notice that in this version of the function that I drew here, or this version of this situation, the point r here, representing the second point or second output value on the tangent line, was higher than the point p. Now that won't always be the case. Sometimes those will be flipped around. And if we had done that, then we would have actually gotten a negative answer for our dy, but we're not really too concerned with the negatives or the positives, so we're just going to put an absolute value on this. Okay? So the value dy is given by f prime of x sub naught times delta x. Now, I know that was a lot we just went through, so if you want to back up the video and rewatch that to try to figure out what's going on, I would highly suggest that. Also, just so you know, this is not something I'm going to ask you to recreate on a quiz or an exam. What's important is this formula and being able to use this formula. Okay? All right, now let's talk about a formula for delta y. And this one's a little more straightforward because delta y, as I mentioned, is just the difference in the output value on the function of x plus delta x and the output value for x. And sorry, that should be x sub naught and x sub naught plus delta x. So to find that value, we're simply going to do f of x sub naught plus delta x minus f of x. And again, we're going to replace the delta x here with dx. Even though we're not dealing with the tangent line this time, we'll have to know that value. So I have f of x sub naught plus dx minus f of x. And again, in this situation we have here, the value for f of x sub naught plus dx is higher than f of x, but that's not always the case, so we'll put the absolute value signs around it. And this would be our answer here. Delta y equals absolute value of f of x sub naught plus dx minus f of x. Okay. All right, so now that we've done that, let's get a little bit more concrete and use this in a problem. So here we're told that we're given the function f of x equals x squared minus 4x, and we're asked to find the values delta y and dy when x equals 3 and delta x equals 0.5. Okay. Now, in this case, this x equals 3. 3 is going to be like our x sub naught. Okay. So that's going to be kind of that starting value of x we're looking at. And then everything else represents the same thing that it did on the picture. So what we can do then to find, and we're actually going to start with finding dy. So recall that the formula for that we found was f prime of x sub naught times dx, which I should also point out, remember that delta x is the same as dx, so we know dx is 0.5. So we actually have one part of this formula, right? We know that dx will be 0.5. And we just need to find f prime of x sub naught, which we can do. So we'll find f prime of x, which will give us 2x minus 4. Then we'll go ahead and plug in our x sub naught. So we'll have f prime evaluated at 3, which would be 2 times 3 minus 4, which ends up just being 2. So we plug that in here. So our dy ends up being 2 times 0.5, and the absolute value of that, which is 1. And so we just get that dy is 1 there. Okay. So fairly straightforward. So now let's find delta y. And we'll again use our formulas. So delta, not d, delta y. So that's going to be absolute value of f of x sub naught plus dx minus f of x sub naught. And let's see. So our x sub naught is 3 plus dx, which is 0.5. So this would be f of 3.5 minus f of x sub naught, which is 3. So we just need to plug both of those values into the function. So we do 3.5 squared minus 4 times 3.5. So we get negative 1.75 here. Minus, if we plug in 3 now, we get negative 3. If we do negative 1.75 plus 3, looks like we end up with the absolute value of 1.25, which is just 1. Okay. It's 1.25, sorry. It's not 1, it's 1.25. All right, and I want to point out something here. If you remember from the diagram, okay, dy, that was the difference between the output values using the tangent line. Okay. Well, that was going to be an estimate for delta y, which was the difference in the output values using the actual function. And note that the two values we got here are fairly similar, right? We have a 1 and a 1.25. Those are not too far off. So that shows us that using dy as an estimate for delta y is pretty reasonable. And you want to pay attention on your homework for this section. Problem that asks you to estimate the value for delta y. And in that case, you'd want to use dy. Okay, and again, this is just kind of a visual for us to think about that. Again, as you see right here, delta y, the difference between the output values on the actual function, but if we're using the linearization to estimate the function, or estimate values on the function, then we use dy as a substitute or an estimate for that. Okay? All right, so let's take this a step further and look at how this might apply in a little bit more of a contextualized context. Contextualized context, that doesn't make any sense. In a contextualized setting, how about that? All right, so let's say you have a sphere and you measure the circumference of the sphere to be 87 centimeters. Okay, so you take out a measuring tape and measure the distance around the outside. Now, whenever you make a measurement, because we're humans and we do error often, there's going to be some sort of error. And so they've determined, whoever's taken this measurement, that there's a possible error in their measurement of 0.5 centimeters, which means they could be off by as much as that. Which means even though they measured the circumference of the sphere to be 87 centimeters, it could actually be some number as high as 87.5 centimeters or another number as low as 86.5 centimeters. Okay, and we don't actually know which of those values it is. And it could be anywhere in between. Okay, so based on that, we want to use linear approximation, or really we're going to use the differentials we were just working with, to estimate the maximum error, which is also called the propagated error, and the calculated surface area. So being that there's possibly error in our measurements of the circumference, if we then use that measurement to figure out the surface area of the sphere, how much could we be off by? Okay, so to start, since we're looking at calculated surface area, we need the formula for the surface area of a sphere. And you guys, of course, all know that off the top of your heads, right? That is, right, as you said, it is 4 pi r squared. Okay. And then they also say that they've measured the circumference of the sphere, which means that maybe the formula for circumference is going to come in handy here. And what's our formula for that? All right, that's 2 pi r. Okay. And now we can get to work. So first thing I'm going to do, I'm going to rewrite the surface area formula. I'm just going to write it as A equals 4 pi r squared. So be careful. I'm not talking about I'm talking about area there, but that's the surface area for the sphere. And as we saw just a second ago, or in the previous problems, that we were dealing with these errors in terms of dy's and dr's, dx's and things like that, deltas, right? Which those d whatever hopefully makes you think of derivatives, which we've been dealing with for a while. So in order to find the error here, we're going to take the derivative of our surface area formula. And since our input variable here is r, we're going to take the derivative with respect to r. So when we do that, what we get is dA dr, so the change in the area with respect to r, would be equal to, and on the right hand side we only have that one variable, the r, so we can take the derivative using the power rule. So bring down the 2, multiply by the 4, subtract 1 from the 2, and we get that our derivative here is 8 pi r. Now, next thing I'm going to do, which might seem a little strange, but again, before we were dealing with dy's and dx's, not like dy over dx. So I'm actually going to multiply by both sides by dr here. Okay. Which if we do that, it cancels out on the left-hand side. And we're left with dA equals 8 pi r times dr. All right, and this dA, in this case, that's going to serve as like our delta or dy, right? So that's going to be our error in calculating the surface area, which think about, again, we talked about how if we need to find delta y, which is the actual difference in output values, that can be approximated by dy. And so that's why we're going to use our dA here to figure out our error, because the dy is kind of like that. That's that error measurement, or that amount we're off, or the difference, right? Okay, now normally at this point, we could just plug some values in, right, and find out what the dA is. But notice what's the problem with that? Well, we don't have any information about the radius, right? We need a dr and an r, and we don't have any of that information given in the problem. So what are we going to do instead? Well, this is where this circumference formula over here is going to come in handy. So first thing we're going to do is take a derivative. Actually, sorry, I lied. Before we do that, we first need to figure out a formula for our radius in terms of circumference, since we have information about the circumference. And we can do that fairly straightforwardly by dividing by 2 pi on both sides here. So we end up with r equals c over 2 pi. Okay, so in a minute we can go ahead and plug that in for r over here. And I'm going to go ahead and write that off to the side for now. Okay, so we got that. And then we also need to find something for dr, right? So in order to do that, I'm going to take the derivative of the circumference function, again with respect to r. So if I do that, I'll end up with dc dr equals, and we do the derivative on the right-hand side. Well, the r has a power of 1. We can bring that down, subtract 1, we'll end up with r to the 0, which is just 1. So it looks like we end up with just 2 pi there. And then again, like we did with the equation for dA, we can multiply by dr on both sides. So these will cancel, and we end up with dc equals 2 pi times dr. And then we can actually solve for dr by dividing by 2 pi. And so what we'll end up with is dr equals dc over 2 pi. Okay. All right, so let me again erase a little bit here and write out the information we have. So using the circumference formula, we have now determined that r is equal to c over 2 pi, and dr is equal to dc over 2 pi. Right? And we can actually plug in numbers for that, right? So for r, we know the circumference of the circle was measured to be 87 centimeters. So we actually have that r equals 87 over 2 pi. And then for dr, well, the dc, that's going to be our error in measuring the circumference, which was 0.5. So we actually have 0.5 as our dc, so we know that dr is equal to 0.5 over 2 pi. Wonderful. So now we can take that information and just plug it into our formula over here for dA. So plug in 87 over 2 pi for r, 0.5 over 2 pi for dr. And when we do that, again, I apologize, I have to erase again to make room for all of this. So what we end up with is dA equals 8 times pi times the value for r, which was 87 over 2 pi times the value for dr, which was 0.5 over 2 pi. Okay, and then we can do some simplifying here. So we can cross out the pi up here with one of the pi's down here. 2 times 2 is 4. That can reduce with the 8 here, so the 8 become 2. These both will cancel out. And across the top, we have a 2 times 87 times 0.5, and the 2 and the 0.5, that will be 2 times 0.5 is just 1. So it looks like we end up with 87 over pi is our dA there. Right, and then we can get a decimal value for that, which would be 27.693. Okay, and so that would be our possible error, or the maximum error in the measurement of the surface area. And in fact, because it's a surface area, we can also put units on here. So this would be centimeters squared. Whew, we made it. Okay, so again, to explain what happened here. So someone measured the circumference of a sphere to be 87 centimeters, and they knew that their error could possibly be up to 0.5 centimeters. Now, if they use that measurement to find the surface area now, we found that the maximum possible error, the maximum they could be off by, in their measurement of the surface area or calculation of the surface area is 27.693 centimeters squared. Okay. All right, one more thing on this is what is called relative error. Sometimes this is called percentage error. And this is kind of like how does that error relate to the actual calculated surface area, okay? So the formula we're going to use for this is d s sub a, or d, sorry, not s sub a, dA divided by the actual surface area, or the calculated surface area. Okay, so the dA we just calculated, and I'm going to use it, leave it as a fraction form for right now. That was 87 over pi. And then the surface area we didn't actually calculate. So the surface area formula, remember, is 4 pi times r squared. And we know we have 4 times pi for the radius. We determined that that was equal to 87 over 2 pi, and we have that squared, which, if we work this out, we'll have 4 pi times, I'm going to leave this as 87 squared for now, over, if we square the 2 pi, that's going to be 4 pi squared. Here, 4's will cancel, one of the pi's will cancel out here. So we see that the surface area is 87 squared over pi, which we could get a decimal from that, but I'm going to leave it like that on purpose for right now. So plug that in up above for our surface area. And so we'll end up with 87 squared over pi. So we have 87 over pi divided by 87 squared over pi. Do some fun with fractions here. So invert the second one and multiply. Okay, notice when we do that, the pi's will cancel. 87 here will cancel with one of the 87s here. So we can end up with 1 over 87 is our relative error. Okay, and from that we can get a decimal. Okay, so we can plug 1 over 87 into our calculator and get 0.0115. Okay, and sometimes it's more helpful to convert that, convert that to a percentage. So what we can do is multiply that by 100, and when we do that, we'll end up with 1.15%. So that would be our relative error. And using these measurements potentially with errors to find the surface area. Okay. All right, that is it for now. Thank you guys for watching.